Now in this problem, we are talking about a compound manometer. It's called a compound manometer because it does have several liquids inside the manometer. When it comes to manometer related problems, we know that pressure on same level on same continuous liquid is same. And we understand that pressure does not change with height for air column. However, for a liquid, pressure at the bottom of the liquid is equal to pressure at the top of the liquid plus H rho G. Now, let's mark several important points on this compound manometer so that we can easily describe what we are doing. Now, what we have to find is P4, but we have to find it in gauge pressure. Now, converting gauge pressure into absolute pressure is very important to understand. Let's say that we have vacuum, absolute vacuum, and atmospheric pressure like this. When it comes to measuring pressure, we can use either of these as our reference point. If we use the atmosphere as our reference point, we call that pressure as gauge pressure. If we are using vacuum as our reference point, we call the measured pressure as absolute pressure. So the difference between absolute pressure and gauge pressure is 1 atmospheric pressure. Now when it comes to compound manometer problems, even though the system looks confusing and complex, what you have to do is apply simple manometer equation several times to all liquid columns. So let's consider this mercury column between points 1 and 2. The height of the column is H3 and the density of the liquid is rho m, mercury density, and we can write the pressure at the bottom of this mercury column is equal to pressure at the top plus H rho G. Similarly, we can consider the oil column and the water column from point 2 to 3 and point 3 to 4. Now what we have to find is pressure of air or P4, and we understand point 1 has 1 atm of pressure. Let's call it as P atm. Now we can refer to equation 3 and we can solve it for P4. We can write P4 is equal to minus H1 rho oil G plus P3. However, we don't need P3 in our solution. So instead of P3, we can write minus H2 rho oil G plus P2, that is from equation 2. In this case, I am disregarding P2 because we don't want P2 in our solution. Instead, I am substituting P2 from equation 1. That's going to be H3 rho m G plus P1. Instead of P1, I can write P atm from equation 5. Now I want the final solution in gauge pressure. So all of these H rho G terms stays same because they are pressure differentials, but P atm measured in gauge pressure is equal to 0. Atmospheric pressure is equal to 0 gauge pressure. So my answer, pressure of the air inside the tank in gauge units are going to be equal to 54.9 kilopascals. Now when you are doing this problem, you have to show unit conversions. However, because of the limitation of space, I am not going to do it here. As I suggested earlier, after solving a problem, box the answer and check whether you completed all the steps to solving a problem. Now, I did not write down my assumptions, so I'm going to write down my assumptions. I assumed G is equal to 9.81 meters per square second when it comes to calculating this answer. And also, I assumed pressure inside air does not change with height. That is why I assumed point 1's pressure is equal to P atm. Additionally, I did not write physical laws for this question. Now I'm going to write it down here. Now I told you the unit conversions are important. Now let's look at the unit conversions. How do we convert H rho G into pressure units? Now let's consider pressure difference between point 1 and 2. For this, height is 0.46 meters and density is density of mercury. Now when we multiply, we get this value. Now what about the units? When I multiply meters, kilograms per cubic meter and meters per square second, I'm getting kilograms per meter second squared. Now we cannot assume that this is going to be pascals. It can be kilopascals, it can be millipascals. We have to make sure that this is converted to proper pressure units. Now let's see how we are going to do that. Now we know a pascal is equal to Newton per square meter. And we know a Newton is equal to kilogram meters per second squared, because F is equal to MA. Now we can write down unity conversion ratios using these relationships. Using the first relationship, I can write this unity conversion ratio, and using F equals MA, I can write this unity conversion ratio. Now if I multiply these two, I can see that newtons are cancelling out, and I am left with a relationship between pascals and kilogram per meter second squared. Now, in my problem, final answer was in units of kilograms per meter second squared. So if I multiply my answer by this unity conversion ratio, my answer would have units of Pascal. Most of the time we express pressures in kilopascals, so we can convert this into kilopascals.